Okay, welcome to Unit 4 lectures. We're going to be dealing with the important concepts of the laws of thermodynamics. We're going to talk about how that relates to biological systems and talk about a connection that we will have with the Unit 9 lab. And we'll be talking about how enzymes work, and then we'll be talking about photosynthesis and respiration, and with respect to respiration, about anaerobic and aerobic types of respiration. And this is how we burn food. Photosynthesis is, of course, how food is made by capturing the energy from the sun in the first place. Okay, so let's take a look at the PowerPoint. Some of the slides are pretty good and pretty self-explanatory, but just to review, potential energy is when something moves to a higher state. You have pushed the ball and used energy to do it up the hill, and once it gets to the top of the hill and is at rest, nothing is happening, that's called potential energy. It's called potential energy, but it's actually stored energy, and in our chemical systems, when there are chemical reactions where electrons move to a higher shell, that means then they move to an orbit that's farther away from the nucleus. It took energy to make them get in that higher orbit. Guess what? They're storing energy. So when ATP is made from ADP and a PO4 molecule, then energy is stored because some of the electrons move to higher shells. But when ADP in plus PO4 is created by splitting ATP, it's like the ball rolling downhill, and that gives off energy. That's an exothermic reaction, and we call that kinetic energy. But it is that energy, chemically, that we use to do work in our bodies, to make our physiology work, to do our chemical reactions, to maintain our body heat, to move our muscles, to talk, and to sense the world around us. So our atoms roll electrons uphill, so to speak, and then roll them back down. And that's the way we use energy. The book also talks about the laws of thermodynamics. And in those, the first law basically says that the total amount of energy in the universe remains constant. I don't know if that's true. I have my doubts. But that's what physicists say. But what I do know is that energy can change from one state to another, but it can never be created nor destroyed. So it's always accounted for. In every chemical reaction, the two sides of the reaction must balance, and they must balance in terms of energy. So, as well as the numbers of atoms of each element on each side of a chemical reaction has to be the same. So we say at the first law, energy can neither be created nor destroyed, but it can change to different forms. And the second law of thermodynamics says the amount of disorder or entropy is increasing. I don't know if that's true. When I make the bed, in the morning, that's not increasing entropy. That's going the other way. That's making it more ordered. So the other slide that shows that remains a little bit nebulous to me. But what we can say is every time energy is used, some is lost as heat. In any chemical reaction, and our whole body operates through chemical reactions, biochemical reactions, if you will, every time it happens, some energy is lost. And so when we move food into our body to make our body, or make more body, or repair our body, then we basically cannot capture all of the energy in that food. Some of it is lost as heat, and that's how we maintain our body heat and so forth. Sometimes the heat can't be detectable. Sometimes it can. So In Unit 9, we talk about these things. We talk about energy webs or food webs. And this is an image that one of the students I had in the regular face-to-face class found, and we put it on the class wiki. And this was a globe class using the same book that you're using. And so in this figure, we're basically showing that there's all these relationships with who eats who. But we have a lab in our Unit 9 in which we have different ecosystems, and we're actually looking at a food pyramid or an energy pyramid. Now, you don't start with this in this lab. You start with a blank slate and little gold dots on this side for every animal. Then you move those gold dots into the right places and check it, and hopefully you get them right. If you don't, you can reorganize it. And then I clicked on pyramid of numbers. You can do that for each of these ecosystems, for the hot desert, deciduous forest, which we have here, Antarctic Ocean, and so forth, just to compare those. But the important aspect of this lab is a question that compares pyramid of numbers with pyramid of energy. Notice that this number here is a sum total of all of these. This is a sum total of all of these. So two of the questions, number 1 and 4, in Unit 9 ask about why the pyramid of numbers might look different than the pyramid of energy. Okay, notice here, this is about 8,000 organisms. This is about 4,500, so we've lost less than 50% in terms of numbers. Here is 1,500, well no, 1,400 actually, so we've lost about 2/3 between this level in terms of numbers. And here's 50 compared to 1,400, so we've lost a lot, a great percentage in terms of numbers. But what if we had only one tree and 20 squirrels and one hawk? So it'd be 121. It would look like the pyramid was upside down. It would be bigger here. Notice the pyramid is always smaller. And so if we look at energy, now we're looking at units of energy, 6,600, 61, and 6. Oh, so look at what happens. If this was 1,000, this is 100. 90% is lost. If this is 100, this is 10. 90% is lost. If this is 10, this is 6. 90% is lost. In most trophic pyramids, if we consider the energy that's transferred between levels, at each stage we lose about 90%. Sometimes we might measure and get 89% or 88%, but it's about 90% is lost, 10% is captured. So if we take a look at a rabbit and we say, well, how many pounds of food does it take to produce 1 pound of rabbit? It takes 10, roughly. How many pounds of food does it take to produce 1 pound of deer? It takes 10, basically. So pyramids of energy are more consistent, and they are always going to be about 90% lost between levels. But pyramids of numbers are not, because the numbers don't represent biomass, they represent numbers of individuals, and one tree could weigh as much as 5,000 squirrels. So numbers, because of body size, can be misleading. And that's actually what the answer should be as relates to questions 1 and questions 4. The pyramid of energy is always smaller as you go up. The pyramid of numbers is not always smaller, and if it is, it may be a different shape because of body sizes. When you get to the first level, which is plants, producers, they gain their energy from the sun. They use the sun's energy to take organic compounds, combine them, raise electrons to higher states, and chemically store the energy that was transferred from the sun. As one animal eats another organism, that energy is transferred to the animal and either used as work or to grow the body, repair the body, or whatever, but a lot of it is lost as body heat or heat of reaction. That's the second law of thermodynamics. Okay? So understand that, because for some reason this is not real clear in your text when you get to Unit 9, and these questions seem to escape students, but they're very fundamental. Don't make it harder than it actually is. Then we also have a lab that we want to look at on enzymes. And we'll just go to that. No, that's not what we're going to go to. Okay, this is going to be a lab on enzymes. In your body, there are certain molecules that are made in the cells. Sometimes cells are specialized to make special molecules. And there are two types that are made on the ribosomes that are both proteins, but one type of protein, or one general category of protein, is structural protein. The protein that makes your muscle cells, for example, are structural. The protein that makes the matrix of your bone that gives your body strength and structure are structural. But there are other proteins that are called enzymes, and their job is to regulate the rates of reactions. If you go to your textbook companion site and click on virtual labs, you can find this lab. And what happens is you can hold to, for an example, in this lab, 37 degrees centigrade, your approximate body temperature is going to be held constant. And these different test tubes are going to have some fluid in them that is all the same, but you can vary the pH and you can vary the amount of substrate. So basically what's in these test tubes is a constant amount of enzyme. When you vary the amount of substrate by adding it to these tubes, somehow I didn't get that one in there. Anyway, okay, and then you can go to the table and see what happens. And what you're going to see happen is, see, I told you I didn't get that one in there. There it is. What you're going to see happen is that the amount of product formed per minute, or the rate of the reaction, is going to go up as the amount of substrate increases to a certain point. And then it's going to stop going up. And the reason is because all of the enzymes are being used. And once all the enzymes are being used, that's as fast as this reaction can go. So you can repeat this with different pHs, and you can see how the pHs affect the enzymes. But the point of all of this unit, or this part of this unit, is simply to show you that enzymes are proteins that affect the rate of reactions in your body that keep you healthy and alive, and that these enzymes are affected by the pH of the cytoplasm or body fluids that they're in. They're also affected by temperature. We've held it constant here. When your body temperature goes up, these enzymes don't work properly and you feel sick. Why does it happen? So that we can hopefully kill the bacteria before it kills us.